Pick it up. You see the drip, yeah, I'm fitted up. Hop in my car and the giddy up. Secure the bag, yeah, I get the bus.
Hello guys, my name is Jimmy and my number matrix is 76646 and I am first year student of Mechanical Engineering at UNIMAS. Today I would like to talk about application of thermodynamics that related in our life. So for this assignment, I choose pressure cooker as my application of thermodynamics.
So before I tell you about the pressure cooker, let me explain about the terms of thermodynamics. So what is thermodynamics? Thermodynamics can be defined as a science of energy. Thermodynamics comes from a Greek word which is therm is means for heat and dynamics is for power. Conservation of energy principle. During an interaction, energy can change from one form to another, but the total amount of energy remains constant. Energy cannot be created or destroyed. So this is the type of law of thermodynamics. The first law of thermodynamics. It is an expression of conservation of energy principle, which is energy cannot be created or destroyed. It can only change form. Second law of thermodynamics. It asserts that energy has quality as well as quantity, and actual processes occur in the direction of decreasing quality of energy. Classical thermodynamics, a macroscopic approach to the study of thermodynamics that does not require a knowledge of the behavior of individual particles. It provides a direct and easy way to the solution of engineering problems. 4. Statistical thermodynamics, a macroscopic approach based on the average behavior of large groups of individual particles. This is the pressure cooker. Pressure cooker applies kinematic theory of gases and the thermodynamics behind the pressure cooker. Pressure cooker allow you to cook food faster or replace energy than a normal cooker by using gas laws to conserve energy and raise the temperature. A pressure cooker locks in the steam inside the cooker so that none of it can escape. The pressure builds in this isochoric process as the volume of the cooker stays the same throughout the process. Under the principle of Gay-Lussac law, P1 over T1 equal to P2 over T2, therefore stating that pressure and temperature are directly related. As pressure increases in the cooker, temperature also will naturally increase. This can also be seen in the ideal gas law. PV equal to nRT because the volume and number of moles are constant. As pressure increases, temperature must also increase to balance out the equation on both sides. This increase in temperature in the cooker heats up the cooker much faster or to a higher extent, thus saving energy and cooking your food faster. We can also look the laws of thermodynamics for the pressure cooker. The first law of thermodynamics states that Q, the heat transfer to or from the system, equals to delta U, the change in internal energy, plus W, the work done by the system. Q equal to delta U plus W, work. Because this process is an isochoric process, as the volume of the cooker stays the same throughout the process, no work is done on the system. Therefore, we can say that for this process, Q equal to delta U equal to 3 over 2 nR delta T. Then, according to the second law of thermodynamics, heat will spontaneously flow from the hot air in the cooker to the food, thus heating and cooking the food. However, some heat will be lost as the cooker is also heated and heat escape side of the cooker. Thus, the efficiency of the cooker will never be 100%. We can also see ideas of transferring heat into the food through a pressure cooker. Heat is transferred from the air and cooker to the food by conduction, convection, and radiation. As the cooker heats up itself, it transfers heat from it, quickly heating up metal, low specific heat to the food through conduction. As the high pressure gas moves around the food is also cooked through convection. There is probably some radiation cooking the food. Also, as electricity is required to run the cooker. As we open up the pressure cooker, large amounts of steam rapidly bursted throughout the rooms as the air moved from an area of high pressure to low pressure. We needed to be careful not to stand directly over the cooker as we release this pressure, so that we were not burned by convection. So the picture below is the resulting stew, as we understood the physics behind cooking it.
So as you can conclude from this assignment, this pressure cooker applies the terms of thermodynamics, which is the first law of thermodynamics and second law of thermodynamics. It is also applies isochloric process, which is the volumes never change. It also applies the ideas of heat transfer, which is through conduction, convection, and radiation. So that's all from me. Thank you. Bye.